Hello all, my name is Ashutosh Rastogi. I'm a teacher by profession. My mission is to impart quality education for all. For that purpose, I'm creating these videos. If you appreciate my work, then please do like my video and subscribe my channel so that I could get the motivation to prepare more videos. Anyways, today in this particular lecture, we will going to discuss about your source coding theorem as well as your Kraft inequality. So these are the outlines. We're going to start up with the introduction. Then we will going to give a brief about your source coding. Although in our earlier lecture, we have already taken a intuitive understanding of source coding. What is source coding? Then we will going to discuss few terms related to your source coding, which are really very necessary to understand the numerical portion. Then we will going to discuss about your source coding theory. What is it? It's a statement. Then we will going to discuss different types of codes which are existent. Then we will going to discuss about your Kraft inequality, and finally we will going to give you the name of two source coding methods. So what are they? And we will going to conclude on that particular note. Most probably in our next lecture we will going to discuss about how we will going to perform this variable length source coding, that is your Shannon-Fano coding as well as your Huffman coding. So in our last lecture we have studied about your basics of information theory, your entropy, redundancy and its calculation, how we're going to do all those manipulations. So we had already studied that. Then in our last lecture we have also taken a basic idea about source coding, and now we will continue our discussion by discussing some basic terms related to your source coding which are very much essential for understanding your numerical portion. And we'll also going to discuss the classification to the different types of codes available, what are they and what are its basic definitions. So let's continue with your source coding. So a conversion of the output of discrete memoryless source into the sequence of binary symbols, that is binary code word, would have been called as your source coding. So we'll be having a discrete memoryless source which will going to generate different sort of symbols, and just in order to convert them into the digital domain, just because our processing demands that we have to have some sort of basis by which we will going to convert our symbols into the digital sequences or binary sequences. So that process would have been called as your source coding. So the device that performs this conversion is called the source encoder. Another insight of your source encoder is we just have to reduce out the redundancy. This we had already seen. So the basic objective of source coding is to minimize the average bit rate. This is what I'm talking about, which would have been required for the representation of the source by reducing the redundancy of the information source. So we basically have to reduce out the redundancy so that we are in a state to maximize our channel capacity, or we can force more and more number of users to use that common medium or channel on the sharing basis. So before we going into the greater details about your different source coding methods, let us understand few basic terms related to the source coding. So first one is your code word length. So what is this code word length? Let x be the discrete memory source with finite entropy h of x, since h is a source and h of x is basically representing the average information associated with that particular source, and it is basically generating x1, x2, x3 up to xm number of symbols or alphabet with the corresponding probabilities of occurrence pxi's, and I goes from 1 to m. That is, for generating symbol x1 it is having your px1 probability, for generating symbol x2 it is going to have your px2 probability, and similarly for generating the symbol x of m it is having your pxm probability. So let the binary code word assigned to the symbol xi by the encoder have the length ni measured in bits. So let us say that here we are saying that your corresponding your symbol xi, the encoder will going to generate a particular coded sequence and its length is your ni. So the length of the code word is the number of binary digits in the code word, or you could say that it is the number of digits or bits that are required to encode a particular symbol. So that is nothing but your code word length. So second important term is your average code word length. So what is that? We had already seen that what is code word length. So this is the total number of bits in your code word. So if you are talking about your average code word, then we have to take the mean of that particular code word length. So the average code word length L, it is denoted with this symbol L, per source symbol would have been given as L is equal to summation starts from I is equal to 1 to M probability of xi ni, if discrete probability would have been given to us, or it is equal to integration starts from I is equal to 1 to M P of xi ni, where this P of xi is your continuous probability distribution. If probability distribution is given to us, then in order to evaluate the average code word length, we have to use this integration formula. And if discrete probability would have been given to us, then in order to evaluate this average code word length, we have to use this particular formula. So the parameter L represents the average number of bits per source symbols used in source coding process. So in upcoming slides, when we're going to see different sort of codes, then we'll came to know that there is a variety of codes where we'll be having different symbols will going to have different number of bits, or we will going to code them into different number of bits. They are not at all uniform codes. So for non-uniform codes, when we have to evaluate this average code word length, then this is the process by which we will going to evaluate the average code word length, or we could say that average number of bits required in your code words. So next point is your code efficiency. So what is that? The code efficiency, which would have been denoted with this symbol neta, it is defined as it is the ratio of L minimum to your L, where L minimum is what? This is the minimum value of code length, and neta approaches unity, then the code word is said to be your efficient one. So if L minimum upon L's ratio is equivalent to 1, it means redundancy will be minimum, and those particular codes would have been called as your efficient code, since the whole objective of your source coding is to minimize the redundancy. So if that ratio turns out to be 1, it means we'll be not having any sort of redundancy, and that particular code would have been called as your efficient code. Then next term is your code redundancy. So what is that? The code redundancy would have been denoted with this particular symbol gamma, and is defined as it is the difference of 1 minus neta, where neta is nothing but your efficiency. So 1 minus neta is basically giving the outcome as your code redundancy. So all these terms are quite necessary to understand, just because in numerical problems we just have to calculate all these terms only. So next is your source coding theorem. So what is it and what it states? The source coding theorem states that for a discrete memoryless source x, which is denoted by your x with the entropy h of x, the average code word length L per symbol is bounded by L will always be greater than or equal to h of x. So source coding theorem basically presents a bound in your average code word length and your entropy of that particular source. So average code word length L will always be greater than or equal to h of x. And further, L can be made as close to hx as desired for suitable chosen code. So it is our desiredness so that we are in a state to minimize the redundancy. Thus, we can say that L minimum should be equal to your hx, where hx is your average information of your source, or you could say entropy of that source. The code efficiency can be rewritten as neta is equal to hx by L, just from the previous definition. So now we're going to discuss about different types of codes. What is its classification? So there are generally 7 types of codes available. Number 1 is your fixed length codes. Second is your variable length code, distinct codes, prefix free codes, uniquely decodable codes, instantaneous codes, and optimal codes. So what are they? We're going to take them one by one. So in most of the cases, all these codes are well understood by their names only, just because their name basically gives us the information about their characteristics. Since if you're talking about your fixed length codes, then in that particular case, all the code words will going to have same number of bits. Variable length codes, here we're going to have different bits associated with your different code words, associated with your different symbols. Then distinct codes, that is different codes, all symbols will going to have distinguished codes. Then prefix free codes, here we will not going to have any prefix, or you could say that in order to avoid the ambiguity, no prefix will be equal to the code word of another symbol. Then uniquely decodable codes, well, all the codes would have been uniquely decodable at your receiving side without having any ambiguity. Then instantaneous code, and finally your optimal code. So we're going to take them all one by one. So before we're going to discuss about that, let us have the insight of this particular table. So here we'll be having a source xi. So it is basically generating 4 symbols x1, x2, x3, x4, and we have presented these 6 coded sequences. So they are basically different formats in which we have represented these code words. So code 1 is basically represented as your 0001, 0011. In the similar manner, code 2, code 3, code 4, code 5, as well as code 6. So we basically try to give the examples of all these codes in terms of these table values only. So first one is your fixed length code. So as its name suggests, a fixed length code is the one whose code word length is fixed. Code 1 and code 2 of the above table, if we talk about this particular table, so this particular code 1 and code 2, if you closely observe that, all the codes associated with the symbols will going to have same number of bits. That is, all of them will going to have this 2 number of bits. This symbol also, this symbol also, this symbol, this symbol, this symbol, this symbol, all symbols will going to have the same number of bits. So code 1 and code 2 of the above figures are above table are fixed length code words with the length of 2. So here length is 2. So next one is your variable length code. So as the name suggests, variable length code is the one whose code word length is not fixed. I mean, for every symbol value, we might have different code word length. So all codes of the above table except code 1 and 2 are variable length code. I mean, if these are the fixed one, then code 3, code 4, code 5 and code 6. In code number 1, symbol 1, 2 is having your single bit, code 3 is having your double bit, and it is your fourth symbol is also having your double bit, or you could say that its length is 2211. So this is the example of your variable length code. In the similar manner, if you observe this fourth code, then here also we'll be having single length code, double length code, triple length and triple length. So here also we'll be having variable length code, and in the similar manner code 5 and code 6, they are the examples of your variable length code. So now next point is your distinct codes. So as the name suggests, a code is distinct if each code word is distinguishable from each other. I mean, there will be no overlapping, or no two code words will going to have the same value. So all codes of the above except code number 1 are distinct codes. So if you closely observe that in code number 1, x1 will be having this coded sequence 00, and x3 also will be having this coded sequence is 00. So I mean, they are indistinguishable codes. That is, if we are receiving 00 at the receiving side, we are not in a state to explicitly mention that whether x1 was transmitted as a symbol or x3 was transmitted as a symbol. So this code is not the distinguished code. Apart from that, if you observe all other methods of codes, or all other codes, they are distinguishable, or they are distinct codes. Next is your prefix free codes. So as the name suggests, a code in which no code word can be formed by adding code symbols to another code word is called as your prefix free code. I mean, in our last lecture we have also discussed about the scope of parsing. What do you mean by that? Just in order to distinguish different code words, we are using a prefix. So there we have described that, but the important point about that parsing or prefix is that parsing should not be same as another code. If that's so, then in that particular case we are not in a state to distinguish different code words. So that prefix should not be like that. So in prefix free code, no code word is prefix of another. This is what I want to try to explain you. So here in this particular table also, code 2, 4 and 6 of the above table are prefix free code. So if you observe that code 2, 4 and 6, here this prefix conditions holds good. Here no two codes is having a prefix which will produce certain sort of ambiguity. So here codes 2, 4 and 6 are prefix free codes. Next is your uniquely decodable codes. So as the name suggests, a distinguished or distinct code is uniquely decodable if the original source sequence can be reconstructed perfectly from the encoded binary sequence. So this is the desirable condition also, that all the codes should be uniquely decodable at the receiver side so that we can avoid the ambiguity and we could also reduce the error. So the sufficient condition to ensure that the code is uniquely decodable is that no code word is a prefix of another. So this is the important characteristics that how we're going to ensure that codes are uniquely decodable. So in order to distinguish different code words, all code words should be of different value and no code word should be the combination of two different code words. So thus the prefix free codes 2, 4 and 6 are uniquely decodable codes. So as this particular table suggests, 2, 4 and 6. So here you will not going to find any particular code whose prefix value is another code word. So now next one is your instantaneous code. So what is that? So a uniquely decodable code is called an instantaneous code. So please keep in mind that instantaneous code will going to possess all the properties of your uniquely decodable codes as we have studied above. So if the end of any code word is recognizable without examining subsequent code symbols. So what is peculiar or different in your uniquely decodable code is that if the end of any code word is recognizable without examining the subsequent code of the symbol. I mean, we are in a state to recognize the end of the code word. So the instantaneous codes have the property that previously mentioned that no code word is the prefix of another code word. That is, it is also containing the properties of prefix free codes also. So prefix free codes are sometimes known as your instantaneous code. Then last one is your optimal code. So when we will going to say that any code is your optimal code. So a code is said to be optimal if it is instantaneous and has the minimum average length L for a given source with a given probability assignment for the source symbol. So if you closely observe that here in this optimal code will be having least redundancy, or we could say that lowest redundancy. So now next topic is your Craft inequality. So Craft inequality basically provides us the basis about the existence of an instantaneous binary code. So it basically gives us a bound by which we can say that whether your instantaneous binary code is existent or not. So let X be the discrete memoryless source which is generating your alphabet just like your or symbols just like your x1, x2, x3 up to xm. Assume that the length of the assigned binary code word corresponding to symbol xi is ni. It means for this symbol x1 will be having n1 number of bits, for this symbol x2 will be having n2 number of bits, and similarly for the symbol xm will be having nm number of bits. So a necessary and sufficient conditions for the existence of an instantaneous binary code is k is equal to summation starts from I is equal to 1 to m 2 to the power minus ni will always be less than or equal to 1. If this particular condition holds good, then only your instantaneous code will going to exist, otherwise not. So this is basically, this bound would have been given by your Craft, and for to honor the name of that person, this inequality would have been called as your Craft inequality. So Craft inequality basically assures us the existence of instantaneously decodable code with the code word length that satisfies that inequality. So I mean, if that inequality holds good, then instantaneously decodable codes get existent. But it does not show us how we're going to obtain those code words, nor does it say that any code which satisfies the inequality will automatically uniquely decodable. So that will be instantaneously decodable, but we cannot say that necessarily if any code follows that Craft inequality, then that particular code is uniquely decodable. So now the source coding method, that how we will going to perform the source coding. So the design of variable length code such that its average code word length approaches to the source entropy is often referred to as your entropy coding. So what do you mean by this particular statement? If you closely observe that here the objective is to compress the source information, and how we're going to perform that compression via avoiding that redundancy or via reducing that redundancy. So if our average code word length is equivalent to or approaches to your source entropy, then in that particular case we will going to have zero redundancy. So this is what we have to do in your entropy coding. So the variable length code which do not possess any ambiguity while decoding can easily constructed by the two methods. And what are those two methods? That is your Shannon-Fano coding as well as your Huffman coding. So in our upcoming lecture, we will going to discuss this Shannon-Fano coding as well as Huffman coding, its algorithms, and how we are going to construct the codes. So hopefully you have got some idea about your source coding and its nomenclature. So in case of any doubt, you can ask me in the comment section. I'll try to solve them as soon as possible. So these are the references. Thank you very much for your patient hearing.